Hello, my name is Bradley Wachtel,
I'm Quentin Bainey Sample.
and we are part of the rear suspension and powertrain group for the SAU Baja team.
In this project, we'll be focusing on designing and manufacturing the rear suspension and powertrain of an SAE Baja car.
SAE stands for Society of Automotive Engineering. SAE puts on a bunch of different design events throughout the world that pertain to Baja cars, Formula racing cars, and even snowmobiles. For our project, we'll be focusing on Baja. So for their Baja design competitions, they have two categories for events. The first category is static. Their static events are mainly structured around inspections of the vehicle and also looking at the cost analysis and things like that. While the dynamic focuses more on racing events such as acceleration, terrain, and endurance races. So part of the components that we have to construct include the powertrain. The powertrain encompasses the engine, CVT, transaxle, and half shafts. Another set of components is the fuel system. The fuel system encompasses the fuel tank and fuel tank mount.
The rear suspension all consists of the suspension members, the bearing housing, the bearing, the coilover shocks, the wheel hub, the calipers, and the wheels themselves. The stakeholders for this project include the committee members Stacy Hanser and Eric Soderstrom, as well as our advisor Dr. Andrew Lutz, and our sponsors Arconic, Cobham, Expert Machining, SAU Design Hive, SAU Student Government, and SAE.
So SAE implements a bunch of regulations and rules that we must follow in making a car for the competition. This is mainly so groups that have a lot of money, they can't buy their way into a good placing, as well as make sure that safe engineering practices are being met. So one of the regulations deals with the fuel tank. The fuel tank that we are allowed to use is a Powertrain SFC 1000. This is the only allowed fuel tank for the competition. Now there are two different mounting methods that we can use for this fuel tank. These mounting methods are mounting method 1 and mounting method 2. Mounting method 1 utilizes two square mounts that the fuel tank sits on with two tubes that connect to the frame, as depicted here. Mounting method 2 utilizes four cantilever members to connect the fuel tank to a tube that connects to the frame. That is mounting method 2. As it turns out, SAE does prefer that you use mounting method 1, but both are allowed to be used in the competition.
Along with that, fasteners for the fuel tank are regulated as well. And SAE requires that we use a grade 5 bolt accompanied with a metallic and rubber washer. And then on the other side of the fuel tank is another rubber washer, and then the mounting that you chose. And then after that is another metallic washer and lock nut. And all of these requirements are true for every club.
So in between the fuel tank and the engine, there needs to be a splash shield. The splash shield is in place to try to divert any liquid or fuel that falls down from the fuel tank onto the splash shield and then off the car. It is important to note that the splash shield cannot extend above any of the fuel tank members, and it also cannot extend outside of the plane of the vehicle. If there are any holes being used for a fuel line, that hole needs to be sealed in a way to where that no fuel can leak through that hole with the fuel line.
They also regulate the engine that you can use, and SAE says that the engine for this year is the Briggs & Stratton 10 horsepower OHV Vanguard Model 19, and then they also regulate what governor position it can be in, and it has to be in position 5, which allows for a 3,800 RPMs from it.
So the general transmission used in this competition is the CVT, or continuous variable transmission. Here's a depiction of the CVT. This is the driving clutch, which comes from the output shaft of the engine, and this is the driven clutch, which is connected to the input shaft of the transaxle. So there needs to be a case on the CVT to not only protect the CVT from mud and stuff during the competition, but also protect fingers for people who are trying to work on the CVT or around the CVT. So these red portions, as denoted here, are for the powertrain. These need to be rigid members or a rigid material, so it could be like a sheet metal or something, but just doesn't allow any kind of mud or debris to get inside of that portion. While the blue is for a finger guard. The finger guard can just be a mesh or something to restrict a finger finding its way in through the side where the CVT is at. So the conceptual design for the powertrain, I'm going to explain just kind of the general workings of the powertrain and the fuel system and everything. So we'll start with the fuel tank. The fuel tank is going to be mounted above the engine because our engine is fed through gravity. From the engine, there will be a fuel line that will go through the splash plate, and from there, it will go into the engine. The engine there will start, and it will produce a rotational motion that will be translated through the output shaft to the CVT driving clutch. From the CVT driving clutch, related motion will go to the CVT driven clutch and into the transaxle. The transaxle is essentially a gearbox, and that will relate motion to the half shafts and then to the wheels.
And then how the rear suspension more or less works is it contains the tire hubs, the calipers, the coilover shocks, and the ball bearings. And the main point of the suspension is to provide shock absorption from the ground and a better driving experience for the driver.
So I'm going to talk about the detailed design and the fabrication process of making the powertrain components or setting up the powertrain components. So the first thing we did was set the transaxle on the engine on the base plate and the engine cradle to see where they lined up. This is mainly due to the fact that we didn't actually design the frame for the Baja car. That was done in a previous year, so we weren't sure what the intended setup for the engine and transaxle was. When both set up on the base plate like this, it is evident that there will be an interference with the transaxle and engine. This made it obvious that we need to elevate the engine so it was no longer having this interference issue. With that being said, two different mounts were created, both kind of a boxy form. The first is engine mount 1. This utilizes two flanges to mount directly to the base plate and holes on top to mount the engine on top. We noticed that it seemed like some wasted material was being used in this mounting method, so another engine mount was created with a similar profile, but instead there was holes cut out on the sides and a slant to the front that cut out unneeded material and at the same time kept the structure of the mount intact. It is expected that it's not as structurally sound, but for the application of the engine being on top, it's not going to cause us any problems. As far as the transaxle goes, it's a pretty easy mount to manufacture. There's actually mounting holes on the half shaft port on the transaxle. With that being seen, we just knew we needed to make a mount that would attach that to the base plate. So it's a very simple mount. Only one was made. It served the purpose very well. So once both in place, here's an image of the engine and transaxle relative to each other. So now that we got the separation that we needed, it was important to get the offsets made for the CVT that the CVT required and that the belt required, the CVT belt. So the CVT requires a 42 millimeter gap from this portion of the driving clutch to this portion of the driven clutch. It's kind of hard for you to see, but it's awkward because you're relating a lateral distance vertically in a way. So to do that, we utilized a caliper and a ruler to relate that distance over from the driving clutch to the driven clutch. By doing this, we knew it probably wasn't 100% precise, but we were confident with how close it wasn't going to cause us a huge issue. The second thing we need to do was get the front to back distance from with the engine and transaxle. This is the distance that's due to the belt. Using the belt that we are using, it mandates that we use a 9.5 inch distance from the 9.5 inch distance from the center of the output shaft to the center of the input shaft. To do this, we found what the distance would be if we just went from the outside diameters of each. Mr. Hanser actually provided us with an aluminum block that was machined to about the precise distance that we would need there. And by inserting the block in between, we were able to get that distance very easily, and then both mounts could be fastened down to the base plate. Once they were fastened down, we were able to put the CVT clutches on and put the belts on. And as you can see here, we have a nice straight line from the driven clutch to the driving clutch. And that's very important because there are some implications that can happen if this was done incorrectly. So if the lateral distance was wrong, we would have rubbing within the CVTs. This would greatly decrease the life of the belt itself. And for the competitions that we were doing, like an endurance race, it would really hurt our time if we had to change belts during a race. And they're also not cheap and having to fund the club. It's just better to save as much as possible. As far as the front to back is concerned, if they were too close together, they would be loose, and that would cause slipping on the belt, and not there would be less rotations related down to the driven CVT clutch. And if it was too tight, it will cause extra strain on the driving CVT shaft, and that would also hurt our efficiency. As far as the fuel tank, as stated before, that is mounted above our engine. We decided to go with the engine mount, or the fuel tank mount that had the 4 cantilever brackets. Although this wasn't the preferred version that SAU wanted us to do, it worked out best for us because we had some scraps that actually were able to be cut and put into the same formation that they wanted with their brackets. With that created, we added a secondary member for it to be mounted on, and then another secondary member on the rear. It was very simple to put on. It is now currently tacked. It just needs a full weld, but it's in place. And SAE also mandates that the engine itself cannot break any of the planes within the engine cradle. And by the use of a dowel rod, we were able to check all the planes, and it is well inside. And as far as rules are concerned, it abides by all of them. So in between the engine and the fuel tank, as mentioned before, is going to be a splash shield. To get the splash shield designed correctly, we had to actually make a prototype. This is due to the fact that we did not make the rear cage, and when it was made last year, it was actually had some human error and it wasn't 100% symmetrical. Because of that, we couldn't use the SolidWorks model for it, as it would give us incorrect measurements. So by use of cardboard, we were able to cut it to the direct dimensions that we needed, place that on some sheet metal, cut that out, and then we had the profile that we wanted. The first idea was to divert as much liquid as possible off to the side of the vehicle. This gave us concerns with liquid possibly going in between the back edge of the splash plate and the firewall. So to combat that, it was decided we would change the orientation to try to direct the flow off the back of the vehicle. This was nice because the tilt of the splash shield would divert it that way, as well as the movement of the vehicle would also pull it back. With this mounting method though, another plate is going to be required. That's going to have to go here to cover the transaxle. That is not going to be a difficult thing to do. A few tabs and it'll be done fairly quickly. It's also anticipated we'll need some angle iron to further ensure that no liquid leaves the path that we want it to take.
And so when we started our designing for the rear suspension, we first started by researching other already existing suspensions that are out there. And so we turned to the University of Wisconsin-Platteville's idea of using double A-arms. And in their design, they utilize a double A-arm, one on top, one on bottom, and separate bearing housing. And what this does, or what this allows, is the A-arms use a hinge method, and this provides a simple rotation of the suspension, and this would relate to an easier mount for the shocks and would produce less stress on the mounts for the shocks. However, when we made a model and put it into our SolidWorks, it was very apparent that this idea probably wouldn't be the best for us because of this rear bend in the back of our engine cradle. And as you can see in Platteville's, their hinges are as low and vertically on top of each other of the car as possible. And this is due to how the A-arm design works, and this just provides the best possible performance for it. And with our current frame, it just doesn't work with this kind of a design. So because of this, we branched off into other rear suspension designs, and we came up with a trailing arm with 2 radius rods. And this one, the bearing housing would be incorporated into the trailing arm itself, as well as all the members would be attached by radius rods. Or not radius rods, they would all be attached by rod ends. And what rod ends do is they allow for greater room of error in the motion of the rear suspension itself. However, it could lead to more stresses felt by the shock mounts while it's in compression. But we think that we have a spot where we can mount the shocks to where it wouldn't make that much of a difference. So after we came up with this design, we tested 2 different possible positions to put the radius rods, or to mount the radius rods. The first was this picture up here. And what we did here is we extended out two members from the curve from before, and we would have to cut these members at a very large angle, and it made this kind of a design not really feasible. So because of this, we made a second design, and which is this one right here. And with this one, we extended two rods vertically up, and this would allow the rod ends or radius rods to be vertically up and down, which follows the profile of how it's attached here, which would be the best performance out of this kind of a design. And after both of these mounts were made, a test was ran with the two to see how the two would perform on the model. And this picture kind of gives a bird's eye view of the car of how it would look. And on the left, you can see here what the radius rods would look like if they were mounted with the first design. And then over here, you can see what it looked like with the second design. And after putting this in the model and moving the suspension around a bit, it was very evident that the second method would be the best. And this is because the radius rods are more parallel with where the half shaft would come out of, and thus it would follow the profile of the half shaft better. Over here, this would the half shaft would want to kick out the bearing housing, and with the radius rod being here, it wouldn't allow that kick out, and that could cause some problems with the suspension while it's being compressed. Whereas over here, where it's parallel, it follows the profile better and allows the trailing arm to swing out along with the half shaft.
Here's the final design. As you can see, some of these are not actually fabricated yet, but I'll explain what the final design is because we had mentioned a lot earlier. So here is the mounting with the engine and transaxle and the CVTs that we mentioned before. That is a plan to be in place. And then here is the rear suspension design that we had talked about earlier. The thing that is not incorporated into here is the coilover shocks as well as the fuel tank. That is simply because they have not been designed yet, but once they are, they will be incorporated into this final design. But this is roughly what our rear suspension and powertrain should look when all fabricated and finished.
So, in conclusion, as of right now, our powertrain has been completely designed and mounted in the engine cradle. The fuel system has been designed and tack welded to the frame, and so all that it's waiting is a full weld, and that should be good as well. The splash plate also is almost all the way done. It just needs a few more tabs to fully secure it to the frame. And then the rear suspension has been fully modeled, and the material for it has been ordered and is in-house, and it's just awaiting fabrication.
So overall, we've realized that this competition and preparing for and designing a vehicle like this has been really good information experience for us as soon-to-be engineers. That is because not only do we get a front-end view of the design portion of the creation of something like a vehicle, but also the front and the back end. So we're actually not just designing, but also building. So we understand how the design portion affects the building portion, which is really important because you can design something that can work in the model, but in real life it might not work because of a whole slew of reasons. And that is really important information for us to learn and has benefited us a lot so far. Here are our references. Thank you.